In this lecture, we're going to be looking at two characteristics of a hypothesis test, the power function and the operating characteristic function. Now recall the following characteristics of a test. Power is the probability of rejecting the null hypothesis. In particular, it's the conditional probability of rejecting the null hypothesis when in fact the null hypothesis is false and therefore should be rejected. Beta is the probability of committing a type 2 error. In particular, this is the conditional probability of failing to reject the null hypothesis when in fact the null hypothesis is false and should be rejected. Now, power and beta are related in the following way. Their sum is equal to 1. Power plus beta is equal to 1, which can be represented in the two additional equivalent ways, one of which I've got listed here on slide 39. Power is equal to 1 minus beta, and equivalently, beta is equal to 1 minus power. Now we will now investigate these two characteristics in more detail. So power is not a single value. Power is actually a function. It's a function that depends on actually several values. It certainly depends on the true value of mu, and when we think of it as a function of mu, we're going to denote it in the following way. We'll use lowercase Greek letter pi to represent the power function, and then we'll list its arguments in parentheses. So in this notation on slide 40, I'm indicating that power, the power function, it's a function of the true value of mu, but it also depends on other characteristics as well, or other quantities as well. It depends on the significance level being used for the test. It depends on the sample size. It depends on the variation associated with the distribution, and so forth. So power is actually a function of several quantities, but to simplify the notation, or to keep it somewhat fairly concise and simple, at least right now, I'm going to just show it as a function of the mean mu. Now, the probability of a type 2 error, which is beta, is also a function of mu, and to express that, to emphasize that it's a function of mu, we will use function notation as well, and so we would denote this by beta, and then with the argument mu in parentheses. Now we can graph each of pi's of mu and beta against mu to get a sense of the performance of a test. The graph of the beta function versus mu is called the operating characteristic curve for the test. And I would also point out that the power function and the beta function depend on the form of the alternative hypothesis. So are we talking about a two-tailed test, or a left-tailed test, or a right-tailed test? The form of the test will determine the form of the power function and the beta function. So the three types of hypotheses that we can test are reproduced below from a previous slide. So we have hypotheses A, B, and C. So again, hypothesis A, this is our two-tailed test. Hypothesis B is a left-tailed test, and then hypothesis C is the right-tailed test. Now, one question that I would ask, and I want you to ponder, is for each of these tests above, what would the power function of an ideal test look like? All right, so we're thinking about the power function now. Remember that power is the probability of rejecting the null hypothesis when the null hypothesis is false and should be rejected. And so for each of these three kinds of hypothesis tests, what would the power function of an ideal test look like? Now, in the following formulas, the random variable z is the standard normal random variable, and beta, evaluated at mu, denotes the probability of committing a type 2 error as a function of the true value of the mean mu. And so for each of these three kinds of hypotheses, a two-tailed test, a left-tailed test, and a right-tailed test, as we indicated on slide 40, the functions, the power function and the beta function, depend on which hypothesis we're dealing with. And so here on slide 42, we have the functions, the beta functions, corresponding to the three kinds of hypotheses. So the beta function, the probability of committing a type 2 error, if we're performing a two-tailed test, that beta function is given by this probability that we've got listed here. And if we're performing a left-tailed test, okay, remember that is hypothesis B, a left-tailed test, then the beta function evaluated at mu is given by this probability here. So, and then finally, if we're doing a right-tailed test, then the beta function is given by this probability. Now note that each of these three probabilities are expressed in terms of z, the standard normal random variable, and that is because the standard normal distribution is the reference distribution for these three tests. Now, we're currently in this situation where we're assuming that we're either sampling from a normal distribution or we've got a large enough sample so that the central limit theorem applies, and the sampling distribution of x bar is approximately normally distributed. And so that is why these probabilities are expressed in terms of a standard normal random variable. So here, we have here, because we know how to calculate probabilities involving a standard normal random variable, we can very simply calculate the operating characteristic function, the beta function, for various values of mu. And but I would also point out and just note here, as I was saying before, not only do these probabilities and therefore the beta function, not only do they depend on the true value of mu, which shows up, you can see where mu shows up, but it also depends on alpha, the significance level used for the test. It depends on the sample size, n. It depends on the standard deviation of the distribution we're sampling from, sigma. And it also depends on the hypothesized value, mu 0. These other two formulas also depend on those quantities. So if we were being technically and notationally completely correct, we would have a list of arguments, not only mu, but we would have alpha and sigma and n and so forth. So you can see that the notation would tend to get somewhat cumbersome. And that's why I'm really focusing on what the parameter or the argument that is of main interest right now, that being mu. So these are the formulas for the beta function for a two-tailed test, a left-tailed test, and a right-tailed test, respectively. And we can also come up with formulas for the power function, either directly, in terms of by looking at what the definition of power is, or we can use the fact that the power function, power plus beta is equal to 1, and so therefore power is equal to 1 minus beta. And we could then use these formulas along with the complement rule and come up with formulas for the power function. So we have the formulas for the power function on slides 43 and 44. And so the power function, if we have a two-tailed test, the power that the test has at a particular value mu is going to be given by this sum of two probabilities. If we are performing a left-tailed test, then the power that the test has will be given by this expression, this probability. And if we have a right-tailed test, then the power function is given by this probabilistic statement. Now, the next several slides give actual power functions. I've constructed these plots in SAS, and they show us what these power functions look like as a function of mu. So here we have the power function for a two-tailed test. So you can see here that the null hypothesis is that mu is equal to some specified value mu sub 0, which the location of mu sub 0 on the horizontal axis is the point at which we've got this vertical line right there. So that point would be mu sub 0. So the null hypothesis is that mu is equal to mu sub 0 against the alternative that mu is different than that. Now, you can see here that when, and by the way, this horizontal axis, this is where mu lives. All right, so these are the number line corresponding to possible values of mu. And we know that for example, for a normal distribution, the domain is the entire real line. So we could consider this going out to negative infinity and also out to positive infinity in the right direction. So when mu is equal to mu sub 0, and so in that case, the null hypothesis would be true, wouldn't it? The probability of rejecting the null hypothesis, which is given by these functions, is equal to, and you'll see here, it's equal to 0.05. And that is the significance level of the test, isn't it? Remember that the probability of rejecting the null hypothesis, when the null hypothesis is true, that is the significance level of the test. The event rejecting the null hypothesis, when the null hypothesis is true and therefore should not be rejected, that event is a type 1 error. And the significance level is the probability of a type 1 error. And so you can see here, and I've got 3 different power functions corresponding to 3 different sample sizes, 10, 30, and 50. You can see that for each of these 3 power functions, when the null hypothesis is true, when mu is equal to mu sub 0, then the probability of rejecting is 0.05, as it should be, because all 3 of these tests are set up to have a significance level of 0.05. Now, for any other value of mu on the number line different than mu sub 0, when mu is different than mu sub 0, the alternative hypothesis is true. The null hypothesis is false. The alternative hypothesis is true. And therefore, we would want to reject the null hypothesis in such a case. And the probability of doing that, the probability of rejecting the null hypothesis when the null hypothesis is not true, is given by the corresponding point on one of these power curves, depending upon the sample size. Now, you can see that when mu is very close but not equal to mu sub 0, there's not a lot of power. The probability of rejecting the null hypothesis is not much greater than 5%. But as mu, the true value of mu, gets further and further away from the hypothesized value of mu sub 0, we see that the corresponding probability of rejecting the null hypothesis increases. And it actually starts to increase very quickly until you get to a point where it's approaching 1, and then it levels off. So for a given value of mu, say, maybe, and you can see where I'm pointing here on the horizontal axis, then if we had a sample size of 10, then the power of the test at this value of mu we would think about just drawing a vertical line through that point and then drawing a horizontal across, and so that would be about 0.26. If we get further away, then the power for that test increases to about 0.55, let's say. You can also see that for a given value of mu, the larger the sample size, the greater the power. So going from a sample size of 10 to a sample size of 30, for that same value of mu, you can see that the power increases quite a bit. And that makes complete sense, doesn't it? Because the larger the sample size, the more information we have from and about the population, and so we ought to have a greater ability to detect the fact that the null hypothesis is not true when mu is equal to some value, say right there. So you see, these are power functions again for 3 different sample sizes. You can see that as the true value of mu gets further and further away from the hypothesized value, power increases it's going to asymptotically approach 1. And the other point is, again, that as the sample size increases for a given value of mu, the power increases. Here is the power function for a left-tailed test. And again, I've got 3 different sample sizes. And so you can see that when the null hypothesis is true, when mu is greater than or equal to mu naught, then there's very little chance that we're going to reject the null hypothesis. And in fact, the greatest chance of that happening is when mu is actually right there on the border, when it's equal to mu naught, and that probability then is going to be the significance level, which in these graphs I'm using 5%. But as mu decreases in this case, so when mu is less than mu naught, and so the alternative is true, then the ability of the test to detect the fact that the null hypothesis is not true, that probability increases. In other words, the power of the test increases. And then finally, this is the power function, or the form of the power function for a right-tailed test. And so again, what I just said about the left-tailed test applies as well, to this right-tailed test. And so you can see how these kinds of graphs can help us understand the performance of a test in terms of its ability to detect when the null hypothesis is not true. Now, given that power plus beta is equal to 1, we know that the beta function is going to be 1 minus power. And so you can very easily visualize what the operating characteristic function looks like, the beta function, by subtracting this, creating a function where we subtract points on this curve from 1. And in fact, the distance between a given point on a curve and this axis, the horizontal line going through 1, is the value of beta. All right, so you can kind of visualize the beta function by essentially flipping this kind of a function, about a horizontal line through 1/2. Okay, so those are graphs of the power function, and again, I want you to think about this question. For each of these 3 tests, what would the power function of an ideal test look like? So I want to show you what these ideal tests would look like, and in particular the power function of these for ideal tests of these 3 types of hypotheses. And so what would the power function for an ideal two-tailed test look like? Well, now remember that power is the probability of rejecting. And so we want to reject the null hypothesis when the null hypothesis is false, but we don't want to reject the null hypothesis when it's true. And so an ideal test would never reject when it should not, and it would always reject when it should. And so for a two-tailed test, all right, where the null hypothesis is that mu is equal to some particular value, and the alternative is that that mu is not equal to that value, then this is what the power function of an ideal test would look like. When the null hypothesis is true, when mu is equal to mu naught, then the power function would be equal to 0. Now I should have a black dot there, and to indicate that that's the value of that's the power when mu is equal to mu naught. Okay, so I've added my black dot there. So when the null hypothesis is true, the ideal test would never reject the null hypothesis. The probability of rejecting would be 0. But for any other value of mu, the probability of rejecting would be 1 for the ideal test. And so this is what the power function of an ideal test looked like for a two-tailed test. Now notice that as the sample size increases, the actual power function is approaching the ideal test. So you can see how those curves are getting closer and closer to this. It'll never look like this, but it is getting closer and closer to that. Now for the left-tailed test, this is what the power function of an ideal test would look like. When the null hypothesis is true, in other words, when mu is greater than or equal to mu sub 0, the ideal test would never reject, right? The probability of rejecting would be 0. On the other hand, if the null hypothesis is true, if mu were less than mu naught, then the ideal test would always reject. The probability of rejecting would be 1. And then finally, for a right-tailed test, the power function of an ideal test would look like this. For any value of mu for which the null hypothesis is true, in other words, for mu being less than or equal to mu naught, the probability of rejecting would be 0. And for any value of mu greater than mu sub 0, the probability of rejecting would be 1. So these are what the power functions for the ideal tests of the two-sided test, the left-tailed test, and the right-tailed test look like. The power function of an actual test will never look like the ideal test, but you can see that as the sample size increases, it's going to approach and look more and more like the ideal test. So let's look at an example. Suppose that we consider a test where the null hypothesis says that mu is less than or equal to 100 against the alternative that says that mu is greater than 100, where the population standard deviation is known to be 5. The test will be performed using a significance level of 5%, alpha equal to 0.05, and a sample size of 25 will be selected at random from this population. Now for each value of mu below, compute the power of the test, and then beta, the probability of committing a type 2 error. So we're going to compute power and beta for 3 values of mu, 100.5, 101.0, and 102.0. And so when mu is equal to 100.5, the power of the test at that particular value of mu, and by the way, let me just point out, this is a right-tailed test, and so when mu is equal to 100.5, the alternative hypothesis is true, and so then we would hope to be able to reject the null hypothesis. But the question is, what is the likelihood of our getting a hold of a sample that will lead us to reject the null hypothesis? In other words, what is the power of the test? Well, that power, that probability, that probability is the power of the function at that value of mu. This is given by the probability that the standard normal random variable z is greater than this quantity. All right, so this evaluates to negative 1.145, and because the standard normal table that we have for the course uses z values that are rounded to 2 decimal places, that's the approach, that's the convention that I'm going to use, okay, in doing these notes. And for assignments and exams, that's what I would want you to do as well. All right, so that we know what we're about, we know we're going to go about doing things in the same way so that we get consistent results. So the power evaluated at 100.5 is approximately equal to the probability that the standard normal random variable is greater than negative 1.15, and that's equal to 0.12507. So there's about a 12.5% chance that when mu is equal to 100.5, or if mu is equal to 100.5, there's only about a 12% chance that we would get a hold of a sample that would lead us to reject the null hypothesis, to detect the fact that the null hypothesis is false and therefore it needs to be rejected. So, and then with the power being 0.12507, the probability of a type 2 error, we can find, using the complement rule, it's just 1 minus the power at this point. And so that would be 0.87497. So when mu, the true value of mu, is equal to 100.5, even though the null hypothesis is false and the alternative is true, there is a very large probability, about 87.5%, that we will fail to detect that the null hypothesis is false. So there's only just a very small probability that we will actually reject the null hypothesis when or if the true value of mu was 100.5. Now, what if we consider, if we move out a little bit further away from 100 in the direction of the alternative hypothesis? So what if mu were actually equal to 101? What would be the likelihood that we would reject the null hypothesis? Well, that is given by the power evaluated at 101. And that turns out to be, and you can see we're doing the same kind of thing here. When we evaluate this quantity, we get 0.645. I'm going to round that to 2 decimal places. And so the power function evaluated at 101 is approximately equal to the probability that the standard normal random variable is greater than 0.65. And from the standard normal table, that is 0.25785. And then we can subtract that from 1 to get the probability of a type 2 error when beta is equal to 101. All right, and so that probability of a type 2 error is 0.74215. So we still don't have a very large probability, a very large likelihood of rejecting the null hypothesis when mu is equal to 101. Well, let's move out a little bit further. When mu is equal to 102, what is the probability? What's the likelihood of rejecting the null hypothesis when that's the case? Well, we see here via this calculation that we've got about a 64% chance, actually. So now we're getting into better territory. We're more likely to reject the null hypothesis than not. The probability of rejecting the null hypothesis when the true value of mu is 102 is 0.64058. And so therefore the probability of a type 2 error would be 1 minus that, or 0.35942. All right, let's continue with another example. We have the same testing situation, a right-tailed test. The null hypothesis is that mu is less than or equal to 100. The alternative is that mu is greater than 100. Again, we're assuming that sigma, the standard deviation of the population, is equal to 5. And we're going to perform the test at a significance level of 0.05. Now, what's varying here is the sample size. So suppose that the true value of mu is actually 102.5. Then for each value of n below, so 25, 50, and 75, compute the power of the test, and number 2, beta, the probability of committing a type 2 error. So for mu equal to 102.5 and a given value of n, the power function, or the formula for the power function of the test, is given by this expression. And notice that because we're allowing n to vary as an argument to this function, I'm going to include it in the argument list. And so the power function evaluated at 102.5 and a given value of n is given by this expression, which simplifies to the probability that the standard normal random variable is greater than 1.645 minus the square root of the sample size over 2. Now, if n is equal to 25, the power of the test is given by that expression, and it turns out to be 0.80511. So if we use a sample size of 25, and if mu is equal to 102.5, then we've got about an 80 to 81% chance of getting a hold of a sample that will lead us to reject the null hypothesis. The probability of a type 2 error would be 1 minus that, or 0.19489. If we increase the sample size to 50, then the power of the test will be 0.97062. And the probability of a type 2 error would diminish to 0.02938. And then finally, if we increase the sample size to 75, then the power of the test would be 0.99643, and the probability of a type 2 error would be 0.00357. So we can see here that as we increase the sample size, the power associated with the test increases, and the probability of a type 2 error therefore decreases. Now let's look at another example. So consider again this test, this right-tailed test, the null hypothesis being that mu is less than or equal to 100, against the alternative that mu is greater than 100, and where sigma is equal to 5. Now suppose that it's required to perform the test at a significance level of 0.05. But we also want beta to be 0.05 if mu is equal to 102. So what sample size is necessary? What's the smallest sample size that would satisfy these two requirements? So this kind of example gets to the topic of designing your study. So again, if we stop for a moment and think about what we're wanting to do, in some context, this hypothesis test is of interest, and we know that in any realistic testing situation, there is always the possibility of either committing a type 1 error or a type 2 error. And as we discussed previously, we know that there's an inverse relationship between these two kinds of errors. For a given sample size, that is, then for a fixed value of n, for a fixed sample size, if we choose to decrease alpha so that the probability of a type 1 error is smaller in a given situation, then the impact, the ramification of that is that the probability of a type 2 error, which is beta, will increase. So by decreasing the probability of a type 1 error, we automatically increase the probability of a type 2 error. On the other hand, if we were to raise alpha, increase alpha, so what would happen is that we're allowing the probability of a type 1 error to increase so that beta, the probability of a type 2 error, would decrease. Well, that's what happens when we have a fixed sample size. What if we want both alpha and beta to be small? What if this is a situation where there are negative ramifications, there are negative costs associated? Well, there will always be negative costs associated with type 1 and type 2 errors, but let's suppose that in a given situation we want both alpha and beta to be small in this particular situation. Now we know that beta is a function of mu, so when we think of this kind of thing, we have to specify at what value of mu do we want beta to have a certain value. So that's what we're talking about here. We're designing a study in such a way that if mu is equal to 102, not only are we performing the test at a significance level of 0.05, but beta will only be 0.05 as well. So there will only be a 5% chance of committing a type 2 error as well. So again, what sample size is necessary to satisfy these two requirements? So the goal is to find the sample size n so that the probability of a type 2 error is 0.05. And so we can represent that mathematically this way. The beta function evaluated at mu equal to 102.5, and actually I've got a discrepancy here, so that's 102. So I think I'm going to have to change my calculation. So let me do that real quick, and then I'll come back. Okay, so I fixed that typo. All right, so again, the goal is to find the sample size, n, so that when mu is equal to 102, the probability of a type 2 error is 0.05. So expressed mathematically, that is written this way. The beta function evaluated at 102.0, that's mu, and then n equal to 0.05. Now, this is going to be the case if and only if the power of the test is 0.95, right? Because power plus beta is equal to 1. So if beta is equal to 0.05, that means that power must be 0.95. Now, recalling the formula for the power, this is expressed, we can re-express this equation in the following way. 0.95 equal to the power function evaluated at mu equal to 102.0 and the sample size n, whatever it's going to work out to be. And so this is the probability that the standard normal random variable is greater than this expression, which involves the unknown sample size, and that simplifies to this expression here. Now, we know from the standard normal table that the probability that the standard normal random variable is greater than negative 1.645 is equal to 0.95. So we have two equivalent probability statements. They both involve, both probabilities are equal to 0.95. Both probability statements involve the random variable z, and both involve z being greater than some quantities. And so that means that these quantities must be equal. In other words, 1.645 minus the square root of the sample size over 2.5, it must be equal to negative 1.645. And so we have one equation with one unknown, which we can then solve for the unknown value of n. And when we do that, we get n equal to 67.65. Now, since the sample size must be a whole number, what we're going to do is go to the next larger integer. Even if even if the formula gave us a value of n, let's say 67.21, we're not going to round down. We're always going to go up to the larger integer. And so the smallest sample size that will satisfy the requirement that not only is alpha equal to 0.05, but beta is equal to 0.05 or maybe a little less, then that sample size, the smallest sample size that would satisfy that requirement would be n equal to 68. Now, here is on this next slide a graphical representation of this problem. And so here again, we've got this right-tailed test. So here we have power functions for a right-tailed test. The null hypothesis being that mu is less than or equal to 100, which is represented here. And the alternative is that mu is greater than 100. And what we want, notice here that I've got a horizontal line at a value of power of 0.95. And so the question would be, for what sample size would, when mu is equal to 102, for what sample size would the power function be at or above this horizontal line at that value of mu equal to 102? Well, I've got several different sample sizes represented here, so a power function for each of these. And I don't have exactly 68, but I do have n equal to 70, and that's the black curve there. And you can see that the power function for n equal to 70 looks like it intersects this horizontal line, power equal to 0.95, at mu equal to 102. Now, we know that if we had the graph for 68, that it would be a little bit better for us. But you can see this is a graphical way of solving this kind of problem. So that is what I wanted to talk to you about in terms of power and beta. And we see that thinking about these characteristics of a test and quantifying them using notation and then finding their probabilistic representations, formulas for these values, allow us to design our experiments that satisfy certain conditions that would be important and relevant in real-world decision-making situations.